Hello everyone, welcome back to my YouTube channel. In this session, we are going to understand the subcellular fractionation and gradient centrifugation. In subcellular fractionation, cells are disturbed and their components are isolated into relatively homogeneous fractions. The first step in subcellular fractionation is breaking the plasma membrane. A high-speed blender can break the plasma membrane and endoplasmic reticulum into small fragments while leaving nuclei, mitochondria, and other organelles intact. The suspension of broken cells is called the homogenate or lysate and is now separated into like components by series of centrifugation, and ultracentrifugation can rotate sample at very high speed over 1 lakh rpm to produce forces up to the 5 lakh time greater than gravity. However, the first spin is usually set at low rotation speed, producing a centrifugal force of about 800 times the force of gravity for 10 minutes. During these spins, the largest and densest material sediment first, forming a pellet at the bottom of the tube. This pellet will contain unbroken cells and nuclei. Thus, an enriched fractions of nuclei can be recovered from the pellet while the other cell components are suspended in the remaining solution called the supponent. The supponent is now centrifuged at higher speed, producing a force of 15,000 times the force of gravity for 10 minutes to sediment mitochondria, lysosome and peroxisome. The supponent contains smaller and less dense components. Recentrifugation of the supponent at even high speed and duration sediments fragments of plasma membrane and the endoplasmic reticulums. A forced centrifugation is still higher speed sediment ribosomes, leaving only the soluble portion of the cytoplasm or the cytosol in the supponent. This series of spins at higher and higher speed and duration is called the differential centrifugation. In differential centrifugation, subcellular components are separated by their size and density, with large and denser components sedimenting faster than smaller and less dense components. The fraction obtained from differential centrifugation corresponding to enriched but still not pure organelle preparation. For instance, some smaller particles will be found in all pellets, considering some of these particles are already present at the bottom of the tube in the original homogenate. A greater degree of purification can be achieved by resuspending the pellets in solution and then performing density gradient centrifugation, in which the sample is made to sediment through the gradient of dense substances such as sucrose. At the top of the gradient, the sucrose concentration is lower than at the bottom of the gradient. There are two main types of density gradient centrifugation: velocity centrifugation and equilibrium centrifugation. The velocity centrifugation, the sample is added carefully to the top of the tube in narrow zone. The sucrose gradient below the sample serves to prevent the concavity mixing of the solution and keeps the particle in tight zone during the centrifugation. Particles of different size sediment through the gradient at different rates, moving as discrete bands. In this technique, the density of sucrose at the bottom of the tube is less than the density of the organelles. So the centrifugation is stopped before the particles can form a pellet at the bottom of the tube. Following centrifugation, the different zones in the tube can be isolated in separate collection tube. A hole formed in the bottom of the tube allows the collection of the different fraction. The fast sedimenting particles emerge first, the slow sedimenting particles emerge later. The other type of density gradient centrifugation is equilibrium centrifugation. In this technique, the concentration of solute in the gradient are very high, such that density of the gradient at the highest point is higher than the density of the particle of interest. Organelles with higher density are defined as having greater mass to volume ratio. During centrifugation, the particles move to the location at which their own density matches the density of the surrounding solution, and this is where they remain. Although larger particles may travel faster to their equilibrium location, and the spin is kept going long enough for the particle to reach equilibrium. Thus, the final state of the tube depends only on the buoyant density of the particles. Equilibrium centrifugation are useful in separating different types of membrane from one another and are sufficiently sensitive to separate micromolecules that are labeled with the different isotopes. A classical example is analysis of DNA replication by separating DNA molecules containing heavy and light isotope of nitrogen using equilibrium centrifugation is cesium chloride gradients. The light and heavy DNA come to equilibrium at different locations along the tubes. A hybrid DNA with the one light and one heavy strand bends in the middle. Thank you for watching.